pressure is force over an area. So with blood pressure, we're measuring the force that blood exerts on the surface area of the walls of the blood vessels. Differences in blood pressure throughout the body keep blood flowing from high pressure areas, like the arteries, to low pressure areas, like the veins. When we say blood flow, we're referring to the volume of blood that flows through a vessel or organ over some period of time. Now, that amount of blood flow from one end of the blood vessel to another is affected by the blood pressure, as well as the resistance, which comes from the vessels themselves. Vasoconstriction, where the vessels constrict and get smaller, decreases blood flow. And vasodilation, where the blood vessels expand, increases blood flow. Now, blood flow is not the same thing as velocity of blood. Blood flow is the volume of blood that moves by a point over some period of time. So let's say that this chunk of blood has a volume of 83 cubic centimeters. And it took 1 second for this much to flow past the blue circle. This would be the blood flow, represented by the variable capital Q. Now, velocity, on the other hand, is the distance traveled in a certain amount of time. So maybe in that same 1 second, a red blood cell at the very edge here traveled a distance of 27 centimeters, meaning it would be moving 27 centimeters per second, represented by a lowercase v. Even though these aren't equal, they are related. And the last piece of this puzzle is area, specifically the cross-sectional area of the blood vessel, which in reality is the same as the blood cross-section, so it should look a little more like this. So based on units, since area is going to be expressed in centimeters squared, we see that the flow rate equals area times velocity. Alright, so as an example, let's say that we want to calculate blood velocity, and we already have a person's cardiac output of 5 liters per minute, which is average for an adult, as well as the diameter of their aorta, which is 2 centimeters. First off, using the equation for the area of a circle, which is diameter over 2 squared times pi, we get 2 centimeters divided by 2 squared times pi, which is 3.14 centimeters squared. Next, since cardiac output is the same as blood flow, we just need to convert this liters per minute to cubic centimeters per second. So there are 1,000 cubic centimeters in a liter and 60 seconds in a minute. So multiplying this all out, we get 83 cubic centimeters per second. Then if we rearrange our little formula, velocity equals flow rate divided by area. And we get about 26 centimeters per second, which also happens to be about 1 kilometer per hour. Alright, so getting back to blood pressure, blood flow, and resistance, that relationship can be written out mathematically as well. So to start, you have an initial higher pressure at one end, as well as a final lower pressure at the other end. The difference between these pressures, or initial minus the final pressure, sometimes expressed as delta P, equals blood flow through that vessel multiplied by resistance. This can also be written as Q equals change in pressure over resistance. So for example, let's say that the blood vessel narrows, which increases the resistance. In order to keep the flow of blood to organs the same, the pressure difference has to increase. And this is typically what happens. This equation might look familiar to a similar equation where change in voltage V equals current I times resistance R, which is also known as Ohm's law, an equation used in electrical circuits. Alright, but let's get back to pressure. Blood pressure is usually highest in a large artery like the brachial artery, which is where blood pressure is usually measured with the blood pressure cuff. And that's because at that point, that blood still needs to be able to push through all the smaller arterioles and capillaries, which means it's going to meet a lot of resistance. In an average adult, blood pressure is about 120 millimeters of mercury over 80 millimeters of mercury. This number might look like a fraction, but it's not. That first number, 120, is systolic pressure, which is the force that the blood exerts on the walls of the arteries during systole, which is when the heart contracts to pump blood through the body. And the second number, 80, is the diastolic pressure, which is the pressure on the walls of the arteries during diastole, when the heart relaxes and refills with blood between heartbeats. And that's why the first number is larger. The arteries are under more pressure when there's more force from the heart pushing on the blood. Now, the mean arterial pressure, or MAP, is the average pressure on the arteries during a complete cardiac cycle, including the systolic and the diastolic pressures. This guy can be calculated in a couple ways. The first is the quickest way, where we assume that about 1/3 of the cardiac cycle is spent in systole, and about 2/3 of the cardiac cycle is spent in diastole. And so we say that MAP equals 1/3 times systolic blood pressure plus 2/3 times diastolic blood pressure. Now, another measurement is the pulse pressure, which is the difference between the systolic pressure and the diastolic pressure. So in our example, it'd be 120 minus 80, or 40 millimeters of mercury. So if we do a tiny bit of arithmetic, we can say that MAP is equal to 1/3 times the pulse pressure plus diastolic pressure, which is exactly the same thing, but just written differently. Now, a completely different way to think about MAP is by using the relationship between blood pressure, blood flow, and resistance. So let's go back to our big artery. Say this time it's the aorta, the biggest of the arteries, coming right from the heart itself. That artery goes to the arterioles and capillaries, let's say representing the whole human body. And then the venous blood returns to the right atrium of the heart. So in this zoomed out view of everything, the initial pressure here represents the pressure in the arteries. In other words, the mean arterial pressure. And the final pressure over here is the pressure in the veins, or the central venous pressure, or CVP, in the vena cava right before they enter the right atrium. Looking back at our equation, pressure initial minus pressure final equals flow rate times resistance. The flow rate is the total blood flow through all of the blood vessels and organs, which is also called the cardiac output, and is measured in liters per minute. Pressure initial is also mean arterial pressure, and pressure final is central venous pressure. And finally, the combined resistance of all the blood vessels of the systemic circulation is called the systemic vascular resistance, or the SVR. So the equation is mean arterial pressure minus central venous pressure equals cardiac output times systemic vascular resistance. Now, central venous pressure is usually a small number, so it's often ignored, and the equation is simplified to mean arterial pressure equals cardiac output times systemic vascular resistance. Based on this relationship, you can see why an increase in resistance, for example, which is mostly caused by arterial vasoconstriction, will cause the blood pressure to rise. Alright, as a quick recap, blood pressure refers to the force that blood exerts on the blood vessel walls. Blood flow refers to the volume of blood that flows through the blood vessels, an organ, or the entire body over a certain amount of time. And resistance refers to the physical or mechanical pushback that blood gets from things like vasoconstriction. What's happening, guys? Thanks for watching. That was a video on blood pressure, blood flow, and blood resistance, which you'll probably notice is a little more of a physiology topic as opposed to pathology. We're going to start getting into physiology a little more here and there, which is fun because I like physiology a lot. I get to work with equations and math, which kind of brings me back to my engineering days. So thanks to Andrea for writing the script on this one and Rishi for editing the script. I did the illustration and the voiceover, and Yifan did the editing. So thanks, guys. It turned out really well, I think. And if you guys want to kind of do a deeper dive on this topic, you should definitely head over to osmosis.org and make an account. We have a bunch of quiz questions and flashcards and other resources to kind of help you study. So if you're interested, check that out. Otherwise, you can help support us by donating on Patreon and subscribing to our channel and following us on social media. All right, guys. See you later.